Hi, I'm Zhao. I'm honored to share our work on privacy-preserving ranked searchable encryption based on differential privacy. This is a joint work with Chungen Xu, Lin Mei, and Pan Zhang. The huge storage capacity and economic service cost of cloud servers attract more and more clients to outsource private data to them. In fact, cloud server is not always fully trusted. Thus, encrypting the data before uploading to a third party is necessary. But this will bring another problem. That is, some common retrieval methods such as keyword search can't be directly executed on server tests. To solve the problems, ranked search was first proposed by Zhang etc. It allows the cloud server to search the top key most relevant documents according to the relevant source between carry keyword and the documents, which has been recognized as the most promising way to realize secure search over encrypted database. And order-preserving encryption is the common privacy protection method used in ranked search. It attempts to preserve the order of ciphertext or numerical data without lacking its plaintext information. However, recent studies show that OPE is vulnerable to many attacks. Differential privacy is a new privacy protection mechanism, which can ignore how much background knowledge the attacker has. It provides a rigorous guarantee of privacy for individuals in a dataset, and is defined with respect to a privacy parameter epsilon. Where lower the value of epsilon, greater is the privacy guaranteed. There are some existing related works on ranked search in order-preserving encryption and differential privacy. Both River etc. proposed order-preserving symmetric encryption scheme, and Wang etc. used OPSE to realize the first secure ranked search. Recent studies show that OPE is vulnerable to many attacks. For example, Grobis etc. introduced new leakage abuse attacks that recover plaintext from OPE or OIE encrypted database. And Onozova etc. proposed that order-preserving encryption is vulnerable to inference attack. Differential privacy is a new privacy protection mechanism. Ducci etc. formally proposed the CAPS or local differential privacy and minimax error analysis framework under local differential privacy. Nowadays, differential privacy has been adopted in many practical settings. For example, we etc. propose the federated learning with differential privacy. Here, we summary contributions of our scheme as follows. First, motivated the need of protecting the rank in searchable encryption. We implement differential privacy in ranked searchable encryption, even if the adversary knows the ranked result. He can infer the privacy information based on the known background knowledge. Although we add the noise to the relevant source between the document and its keyword, we can ensure the accuracy of search results with high probability. And compared with existing ranked search schemes, our scheme will not reduce the search efficiency while ensuring high security. Before introducing our scheme, let's explain some primitives used in this paper. First is the order-preserving function. For sets A and B, a function f is order-preserving if for any I, j in A, fa is greater than fg if and only if I greater than g. And the second is the order-preserving encryption. For plaintext space D, ciphertext space R, and key space K, we see a collection of three polynomial time algorithms is order-preserving if the encryption algorithm is an order-preserving function from D to R for all key output by key generation algorithm, which can be described as follows. The third is epsilon local differential privacy. Randomized mechanism Q satisfies absolute local differential privacy if and only if for any two inputs x1, x2, and any possible outputs y of Q. We have the following equation. And the first is the Laplace distribution. The distribution with following density function is called Laplace distribution. And TF and IDF row is always used to evaluate relevant source in information retrieval. Here, the TF refers to the number of times for a given keyword appears within a document, and IDF refers to the importance of keywords in the whole document collection, which can be obtained through dividing the cardinality of document collection by the number of documents containing the keyword. We choose the following formula to calculate the relevant source, SIG, between a document FI and a keyword WG. Here, FI denotes the document and WG denotes a search keyword. This FIG denotes the TF value of WG in documents FI. N denotes the total number of documents in the collection, and FWG denotes the number of documents that contain the keyword WG in the collection. Now, I introduce the system model firstly. There are three roles in our DPRC scheme: data owner, data user, and cloud server. The data owner and user are fully trusted, and the cloud server is honest but curious. That is, the cloud server will execute the cryptographic protocol correctly, but it will try to learn the privacy information from the executive process. And the data owner first extracts the keywords from a collection for documents, then calculates the relevant source between each document and its keywords. After that, he builds a secure encrypted data index and outsources it to the cloud server, together with the ciphertext of documents. When the data user wants to search the document containing a specific keyword, she first gets authority from data owner and obtains the secret key, then generates the trapdoor and submits it to the cloud server. Upon receiving the trapdoor, the cloud server is responsible to search the index and retain the top key most relevant document according to the relevant source between the search keyword and its documents. Then I explain some notions used in our scheme. We let Q be the carry function, which inputs a carry keyword W and then outputs key sources of the top key most relevant document in a collection of documents if. And then we define the notion delta Q is as follows. So the disturbed relevance source of the document FIG is as follows. Here, the FIG is the gist document in a sequence of documents containing keywords WI. To avoid the cloud server recovering the original sources according to some statistics of disturbed relevance source, we use OPE to encrypt the disturbed source SIG to ESIG before outsourcing to cloud server. We define Q is a function which inputs the search keyword WI and then outputs key encrypted relevant source after being disturbed of top key most relevant documents. Now I give the definition of our DPRC scheme. There are four algorithms: key generation algorithms, building index algorithms, trapdoor algorithms, and search algorithms. Now, I introduced these algorithms in detail. First, For the key generation algorithm, the data owner inputs secret parameter length and outputs secret key as key. For the building index, the data owner first calculates the queue corresponding to the document set F, and then for each keyword, randomly selects lambda bit string key R0 as the encryption key of NRY. For each document containing WI, the data owner generates an encrypted disturbance relevant source ESIG by adding noise drawn from a Laplace distribution and using OPE to encrypt it. Next, NIG word is stored in a search area A. Meanwhile, the secret key and the location in A of NIG are stored in a search table T. To avoid revealing the number of distinct keywords in F, we pad the remaining entries in T and A with the random string. Finally, the data owner generates a sequence of ciphertext C using the secure symmetric encryption algorithm and send I and C to the cloud server. For the trapdoor algorithm, when a data user wants to search some documents containing the keyword W, she first gets authority from data owner and obtains the secret key, then generates the trapdoor about the keyword and sends it to the cloud server. When receiving the trapdoor, the cloud server first uses it to obtain the first node information about the keyword W, and repeating the following operation to obtain the information about a document containing the keyword. Finally, the server stores documents according to their sources ESI and returns the top key most relevant documents to the data user. Here is a security proof. Through the proof process, it can be concluded that our DPRC scheme satisfies epsilon local differential privacy. To clearly demonstrate the efficiency and accuracy of our scheme, we implement our scheme on a personal computer. Picture A and Picture B show that the time cost of building index increases with the number of documents and keywords. When the keyword and the ID of document pair reaches 500,000, the time cost of building index is less than 14 seconds. Compared with its existing schemes, our scheme takes a little longer to build the index, because we need to add noise to the relevant source. And from this picture, we know that the search time increases with the number of documents containing the carry keywords, and compared with existing ranked search schemes, our scheme doesn't bring too much time cost. And from these pictures, we know that the higher value of epsilon, the higher accuracy. When epsilon is equal to 1.2, the accuracy of our scheme can reach 94%. Motivated the need of protecting the rank in searchable encryption, we propose a privacy-preserving ranked search scheme based on differential privacy. We use a differential privacy protection model to protect the ranked information in ranked search by adding nodes drawn from a Laplace distribution into a relevant source to disturb the real source. So even if the adversary knows the final ranked results, he can't infer the plaintext information combined with the known background knowledge. The experiment concludes that although the ranked search is disturbed, it can ensure the accuracy of search results with high probability. In the future work, we will construct a DPRC scheme that supports multi-keyword search and dynamic street. Thanks for your listening.